Assalamualaikum and good day everyone. Continuation from previous class, I would like to show you another example on how to use a poll assignment method for a simple problem such as in this shown in this example. For example, you are given a system with an ARCS model with the first order ARCS model bz minus 1 over 1 minus a z minus 1, and you are given a value of a and b as such, or maybe you are given a problem asking you to identify the value of a and b using your least squared method. And as soon as you obtain this value, you need to design pole assignment controller, okay, so that the system will always have a stable pole at t equals to 0.5, for example. Okay, so this is an example of problem. So what can we do and how can we actually solve this kind of problem? Okay, let me just show you step by step on how to do it. So if you remember from yesterday, from previous class, okay, so we have our input is now becoming it is over here, it's going to be R, a reference input that we put. Okay, and then we're going to design a controller here. It was H node if I'm not mistaken. Okay, and then this is our system as before, b z minus 1 over 1 minus a z minus 1. Okay, and then you have another controller at your feedback here with the value of g node. So it is as simple as this. Okay, and this is a negative feedback system. All right, so this is the signal, then you have your u here, isn't it? Okay, now so before we can actually define the design controller, you have to remember the two objectives of this problem. Is the first one is to ensure that the system is always having a stable poles, and the second one is actually to ensure that the system is having steady state error of 0 at all the time. Okay, so for a stable pole, you need to have the system characteristic equation of the system equate to the value that given to you in the questions. All right, so before we can do that, we need to find the overall closed loop system equation of this problem. So let's derive the closed loop system equation. So you have your y is equals to bz minus 1. I'm not going to put the value first. I'm just going to solve the problem as it is. Then later I will just substitute the values. Okay, multiplied by u, and at the same time you know that u is equivalent to rh naught minus yg naught. Okay, so then you're going to substitute u into y, so you're going to get y is equals to bz minus 1 over 1 minus a z minus 1 multiplied by rh naught minus yg naught. Okay, of course all of this in a zero order whole or z domain. I'm not going to put it there, but you are most welcome to put if you like. Okay, but I'm just going to write as it is, but I know that all these variables are in z domain. Okay, so then you can expand this equation by multiplying y with 1 minus az minus 1, and the bz minus 1 is multiplied with rh naught and gy naught. Okay, okay, so since I have y over here on the other side as well, I'm going to collect all the y together. Okay, right, then we can factorize y again. All right, okay, therefore your y is actually equals to B H naught Z minus 1 over 1. I'm going to collect the A minus B G naught. I'm going to collect the negative outside the factor. I'm going to factorize it as such. Okay, and I'm going to put the Z minus 1 at the outside of it. Okay, and of course this is multiplied with R. Okay, the input of my equations. Alright, so now we have this as our first, this is our closed loop system equation. Therefore, the first design rule is to ensure stability. Okay, to ensure stability, we need to write the closed loop, the characteristic equation. So we take the characteristic equation. In this case, the characteristic equation is the denominator of your closed loop transfer functions. So take that value and find what is your poles, okay, by equating it with your poles, all right? So actually what I want to say here is by equating it with the pole from your characteristic equation. Okay, not by equating with the characteristic equation. All right, so the characteristic equation is 1 minus A minus B G naught Z minus 1. This is equal with 0 to find your poles. All right, and then you know that Z minus 1 is actually equals to 1 over Z. So if I do that, okay, I'm going to get this one is equals to 1 is equals to A B G naught Z minus 1. So that Z minus 1, if I change it to 1 over Z and bring it to the other side, then I will get Z is equals to A minus B G naught, B G naught, that's all. Okay, so this is the poles of your system. So right, so what we can do is then we can assign this pole to be 0.5. So how to do that? We can just say that A minus B G naught is equals to 0.5. That's how you do it, all right? Okay, so straight away from here, we can find our G naught because that is your controller. That is what the value that you like to know as a function of A and B. So you can see that it is as a function of your parameter of your system. Okay, so you can have that the BG naught in a positive sign by rearranging this equation is going to be A minus 0.5. Okay, therefore G naught is equals to A minus 0.5 divided by B. Okay, so you can put this equation in programming. You can put it as part of your programming for least square or recursive least square. For example, you remember when we do our programming for least square, within that loop of finding your parameter A and B, you can then define the value of your controller as a function of A and B. Therefore, every time your least square change the value of A and B, when your parameter of system changes, you will actually update the controller of your system as well. So I will show you that in the next class, okay? Right, so then you already get the value of G naught. You can just substitute the value by having your value of A, which is, if I'm not mistaken, what is it just now? A is equals to 2, B is equals to 1. Okay, so you can just put that the value of A equals to 2, 2 minus 0.5 divided by 1. So that's going to give you 1.5. Okay, that is the value of your G naught. All right. Okay, how about your H naught? H naught coming from the design rules number 2. The design rules, this is design rules number 1. to ensure stability by assigning the pole specific poles. Okay, so design rules number 2 is actually to ensure the steady state error is 0. Okay, how to do that? Of course, your y must be equals to r. Therefore, your y over r must equals to 1. Okay, so we have our closed loop system equation just now. All right, so we can take that closed loop system equation that we already derived, which is this value that we have here. Y is equals to that thing there. We can just copy that and then bring to the other side here. Okay, so we can use that. Okay, and then I can write this y over r is equals to bh naught z minus 1 divided by 1 minus a minus b g naught z minus 1, and I would like to have this all equivalent to 1. Okay, and why do we want it to be equivalent to 1? Because of the definitions of steady state error. And also you have to remember when we want to measure the steady state error, if it's in time domain, of course we want to measure it when time is approaching infinity. In Laplace domain S, we want to do it when S is approaching 0. And with Z domain, it is happening when Z is approaching 1. Okay, so that's what you have to remember. You can refer this to any textbooks to find out about it. So this is happening when, if it's in time domain, when t is approaching infinity, in S domain when S is approaching 0. So similarly for Z domain when Z is approaching 1. Okay, so that's what it is. I'm going to erase the rest of it. Just stick with Z approaching 1 by creating Z need to be equivalent to 1. Okay. Okay, so what we can do then, just substitute the value of Z equals to 1 into the equation. Of course, Z minus 1 will also become 1 because Z minus 1 is simply equivalent to 1 over Z. So then what you're going to have left into this equation is BH naught divided by 1 minus A minus B G naught. Okay, those things is equivalent to 1. You already have your G naught. You know your A and B, that of course it's changing with time, but every time it changes, you can capture this value and then you can put into this controller so that your H naught can be updated as well. Therefore, straight away you can know that H naught is equals to 1 minus A minus B G naught divided by your B. Okay, so this can be evaluated by giving all the value 1 minus, you know, A is equals to 2, B is equals to 1, G naught is equals to 1.5. Okay, so 1 multiplied by 1.5 divided by B is equals to 1. So I'm going to have 2.5 minus 1, 2 minus 1.5 is 0.5. 1 minus 0.5 is another 0.5. So you have 0.5 divided by 1, it's 0.5. So that is the value of your H naught. So you can then put this value into your controller and your controller will be updated. Your controller will be able to perform the controller with a stable pulse at the all time, and also with the value of your steady state error become 0. Okay, so this is one example of a simple pole assignment method.